Okay, so today's tutorial is about M4, and this will be our last tutorial. So milestone 4, as you should already be seeing from the lectures, we are doing the traveling courier problem, where we have multiple depots, we have multiple pickup positions and multiple drop-off positions, and you'll need to find out the fastest delivery route to cover all of the pickups and drop-offs. How do we do it? We will first need to estimate the travel time between all of the locations and store it. And then using that, we will need to find a good delivery ordering using some kind of algorithm. And we will then return the final tour that's found by your algorithm. And everything in less than 50 seconds. So in theory, you'll be able to do everything like brute force way, but it will take forever. So algorithms are there for your time constraints. So your first sub-problem, estimating the travel times between all of the interesting positions. We will need to eventually build something like a matrix. We have the columns as from intersection and rows as to intersection, or other way around. Other way around. This is the rows, this is the columns. For the first option, we can estimate by distance, which is really fast because it's just a computation, one single computation. But it will be inaccurate because it doesn't take into account of any path. Option 2, we can compute the exact path by your Dijkstra or A-star algorithm from M3. This is accurate, but it's slow because Dijkstra is slower than one single calculation, and you will be doing this for a lot of intersections. If we want to do it by computing the path, this is the most naive way, which is we do it for all of the source intersections. We do it for all of the destination intersections, and we compute the travel time, the path between those. And this will take the number of sources times the number of destinations times your A-star algorithms complexity, which is, we say we have K depot pickup drop-off interstate intersections, and we have V total intersections. What will be the complexity? So first, how many source intersections do we have? We don't really need to compute for all of the intersections because we're only interested in K. Yep. And destination? Yeah, they're the same things. So we have K squared and find path. What's the complexity of find path using A-star or Dijkstra? The complexity of Dijkstra is V log V. So everything together is K squared V log V, which is very slow. On large test cases where K is greater than 300, it will be very, very slow. How do we speed up then? We know that Dijkstra can do multi-target pathfinding, right? From one single source and you run Dijkstra, you will get the path for all of the targets that you have. So this will be from a single Dijkstra, and you only need to go through all of the sources. So in this case, we only have k v log v compared to k squared v log v. Algorithm-wise, that is the most we can get. What if we want to get even more speed? Let me correct it. Algorithm-wise, that's the most we can get with the most accurate estimations. If you can sacrifice some estimations, then you can get even faster, but that's your choice. What if we want even more speed from this? We can do parallel programming. So this is just a graph to motivate parallel programming. This line is the amount of transistors that are on chips in time. So from Moore's law, this will grow and grow every year. But while this is growing, your single thread performance, program performance is degrading. Your frequency is degrading, and the power and number of cores are saturating. So, which is why working more on single-threaded performance is not as desired at this point. At this point, we want to take in the advantage of multiple cores. So your processors these days now become multi-core processors where you can get multiple cores. This is just an example of 4 cores, and all of the cores will share the same memory like this. Each core can execute its own instructions, which means that you can have multiple instructions executing at the same time. And all of them will share a common memory space. In all of the programs that you are writing till today, you're using a single core with the shared memory. Most applications use one thread, and you have been taught to write single-threaded applications. Single-threaded applications do not need to worry about sharing memory because you are the only one using it. But if you have multiple threads, you will need to worry about the memory sharing because multiple threads can be writing or reading the same memory. And you don't want that to mess up with your program execution. This is EC 243 stuff. In each of your cores, you will have a program counter, a PC, a stack pointer, SP, and your program counter will point to somewhere in your instructions code, and the instructions are stored in memory. This is your virtual memory space. The first chunk of memory is always your instructions or your code being compiled into machine code. The next chunk, global variables, heap variables, dynamically allocated memories that are growing in this way. Your stack pointer is pointing to the stack located at the bottom of your memory block. Right? if you have multiple cores, each core will have its own program counter and stack pointer. Your program counter can be pointing in the different instructions in the instruction memory chunk. And this instructions is shared because you're only reading from it. You're not writing to it. So it's safe to share it. And your stack pointer will be pointing to a different chunk of stack. So each core you're using will have a different stack. And the stacks are storing your local variables. And the stacks are not shared, which means that you don't need to worry about writing to stack at the same time as someone else. However, your global variables and your heap variables are shared by all threads. And that's the things you'll need to worry about the most. So this is just repeating. Each thread has their own program counter. It can be executing a different function. It's almost always executing a different instruction. Each thread has its own stack. Each thread sees the same global variables and dynamically allocated memory. So this implies that if needed, you can make the threads communicate through memory because they will see each other in the global variables and the dynamically allocated memory in the heap through pointers, which means the communication can be fast. But you must be careful that they don't conflict in reads and writes to the same memory. If the two threads try to update the same global variable at the same time, if they try to do that, you won't know which update wins. That's totally random. And it can mess things up. And you can have more threads than CPUs because your CPUs can decide which thread to run, which thread wins the CPU. And this is usually determined by your OS or by some hardware microarchitecture algorithms that you don't need to worry about as a software programmer. But you have to worry about how many threads you create under which circumstance that can make it run faster. Because sometimes it might run slower with multi-threaded. So these are the theories on multi-threading, and these are how to write it. You have two options. The first option is using OpenMP. So at the program start, your main function starts with the first thread, which is the main thread. And if you need more, you can either use OpenMP, that is a higher level code that's run by the compiler, decided by the compiler, and it will compile and run serially if the compiler doesn't support OpenMP, but our computer support it, so you can just use this for a for loop, and your compiler will then split the for loop into different chunks according to how many threads it can run. You can also use C++11 threads, the thread function, the thread library, which gives you more control. You can tell the code what to do in this case, but it's lower level code, which means more coding. And I think some of you might already be doing this. Yeah, really crowded classroom today. Yeah, I think some of you might already be doing this. You can use the thread library in C++ to load your street map and database and your OSM database at the same time using multi-threading. And this is just creating a thread, loading it, and joining. So these are just the two ways of programming using multi-threading. First, loop parallelization with OpenMP. If we have a loop like this, we can make it multi-threaded by just adding one single line above it. Pragma OpenMP parallel 4. And this will split this loop into 0 to 25, 25 to 50, 50 to 75, and 75 to 100. This will split it into continuous chunks. By the way, anyone knows why they are continuous chunks? This is some advanced stuff that's related to computer microarchitecture. So each core will have its own cache. And when you are reading from the cache, usually the cache fetches one page of memory from your memory, shared memory, and store it inside your cache. So, and one page of memory usually is more than one variable. And that's usually in continuous order. So splitting the for loops into continuous chunks will make like the fetching from the shared memory into a cache less frequent. So this will be significantly faster than doing like 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So yeah. And then following calls down will join all of the threads. Now let me do the first demo. Let's take a look at this program. So to use OpenMP, you'll need to include the OpenMP header. And what this program does is that it has a vector length of 1000, and it creates 3 vectors with 1000 length. It will first initialize the vectors, and then we will time the second part, which is we're doing something to A and B and storing the result in C. And this is just to get the compiler to not optimize out the for loop. So first we'll comment out the OpenMP line, and we'll see how it does as a single-threaded program. We have a total of 1 thread, and the elapsed time is 34 microseconds. Now, if we enable multi-threading, make and run. We're getting more. We're getting more time. Anyone knows why? We're using 16 threads, but we are slower. Could be. Let's comment out this line and see if this helps with anything. Nope. Doesn't really help. Yeah. So creating the threads probably takes time. So let's try to make this length larger. And try again. So this is without multi-threading. No, what did I do? Okay. This is with multi-threading. So we're getting a speed up there. If we add on more zeros, let's remove this and see. Yeah, we are getting more and more speed up. And you'll see that the speed up will eventually converge to 8. And why is that? Let's look at our CPU status. LS CPU will give you your CPU information. So we have information about your architecture, your address sizes. You have 16 CPUs with 8 cores and 2 threads per core. We have 2 threads per core, means that you can create 2 threads per core, and the 2 threads will share the same core. But in this case, it doesn't really help because we're converging to the 8 core limit. Because the operation we're doing is the divisions, multiplications, and stuff. So if you have 2 threads per core, the functional unit that does the division and multiplication will be limited. So they will need to still wait for the other one to finish. So it doesn't really help much in this case. But it will help if there are no shared resources that's exhausting. And yeah, any questions about this demo? I'll go back here. So these are the times that are measured with a machine that is not loaded. So as we already see, if we don't have a large enough vector length, we are actually slowing down with multi-threading because of multi-threading overhead. We have significant overhead to start the threads, so which is why we need enough work to amortize this. And parallelizing can actually slow you down in a lot of cases. Okay, now we have this program where we have two vectors. We're adding them together. So we have one vector with 50, one vector with 2, and we want to add them together and store in A. So A will end up having 52s. And then we are outputting everything to the terminal. If we convert it using multi-threading, convert the two for loops. And because A and B are declared before multi-threading starts, they are shared memory. And because the integer i's and everything inside the for loops are declared after making them parallel, these are local variables that are not shared. What will the program output be? So we're adding them in the first for loop, and we're outputting A in the second for loop. Okay, let's keep that question and let's do a typing speed contest. I need two of you to do it. Who wants to do it? Like I brought a separate keyboard. So one of you can use my computer and the other one use the keyboard to hook up onto my computer. And whoever can type, I am an amazing electrical and computer engineering student because I am a great typist, and program is mostly about typing speed. I'll need two of you. Uh, so one of you can type in one window and one the other, or you're fighting. You're fighting over this. No.
Wait. Oh. Where do I look at that?
Okay.
Oh. Where am I? Huh? Okay. Wait. Alt tab. Where'd it go? Where'd it go?
Yeah.
It goes to the PowerPoint though. Like, now if I just do it, right? No, I'm controlling it. Nah, it's too hard. We can think of the goal.
Just do it once.
All right.
Yeah.
Okay. Can I take the right side?
Yeah.
Okay. What's the thing that we're gonna type? Okay. Hi, Anna. Hello. Okay. Oh. All right.
And because you take the computer, you can use mouse.
Yeah. So you're always on the right side. But we can collaborate. We can't collaborate really. Okay.
Yeah. I think you got the idea. I think you got the idea, and let's think about what will this program output be. Through a demo. So we have this program, and let's make and any expectations on what the output will be? Yeah, like what you just did. Random stuff because multiple threads are fighting over the same resource. Yeah, it's messed up because we are printing. And the print stream, we only have one print stream, which is the standard output to the terminal. How do we fix it? First, let me show you, can we actually fix it without using multi-threading? Which I guess you should know that this is what we should get without multi-threading. Let's add back multi-threading. Let's time it. 0.173 micro. Let's remember this. And I'll make the print statement a critical section that multi-threading should avoid. And let's then do it again. So now we have the right print statements. Just the order is messed up because of multi-threading, but that's okay because we're doing it with multi-threading. And the time is not as expected. Let me switch a machine because this one is loaded. You just switch to another machine that's less loaded. I'll do it without the critical and make and time. And I'll do it with the critical. Make and time. Okay. We're not getting the right things, but you could get the idea that critical will make it slower because we're waiting for it, actually waiting for it to finish. But it will get the right output. Yeah. So this is what I just showed you. You can use multi-threading for this for loop, but in order for it to not mess up with shared resource or shared memory or anything that's shared, you can make things that you want to make critical. You can make things that you don't want to be parallelized critical, so that each thread will wait for each other to finish. This means that we are putting a lock inside the section. It's for a section, I think. Uh, I'm actually not too sure about that, but you can try surrounding them with that. Yeah, this marks a block that's surrounded by brackets. You can surround them by brackets and see if it does anything, because it's done by the compiler. So yeah, making them critical will just means that we're putting a lock there and only one thread can grab this lock at the same time. But making everything critical will destroy your performance because it's serial, essentially. Next, back to our milestone 4. Fast path binding. So here are just the times measured by us with like n equals to 175 and d equals 20, and these are the speed ups that we measured. So if we do the iterative A star, we get this amount of seconds. A parallel iterative A star will speed it up by about 8 times. Multi-target Dijkstra speeds it up by 33 times using algorithm only. If we make it parallel, we can then further speed up by about 8 times compared to the algorithm one. So we finally get a 250x speed up, which is why we will need to first tune your algorithms to the best you can get before parallelizing. How do we parallelize the multi-destination Dijkstra? We first have a for loop that finds paths from source to key intersections. And then the find path helper function is then defined here, running Dijkstra. And here are three global variables that we have here. So this code makes sense, right? We have the global variables here. We have the for loop that runs multi-destination Dijkstra for each of the source that you're interested in, and you're storing everything into the path. Into your final matrix, right? Next thing, we want to parallelize this by adding the open empty parallel for before the for loop. And this will run the path in parallel. But will this work? Think of shared memory. Will this work? If we just do it for multiple sources and we do it with multi-threading, which means that we are calling a bunch of fine paths in parallel. Will this work? If you look in here and here. Yeah, in here you're pushing to the same shared priority queue, which means that you're modifying the shared global variables. And to not do that, we move the priority queue and the vector of nodes inside find paths. So now they are local variables that are not shared. And in here, we're just modifying private copies. Now, what about the last one? Is that okay? Is this one okay? Is this one okay to be left as global? Yeah, because we're only reading it, never written. Let's consider this case. We're inside this function and we have the same code, but this time these two are local variables, not global variables. Is this okay to leave them outside? And wavefront and nodes are passed by reference. we have local variables, but they're passed by reference into the function that's modified now. So all of the variables that are declared before the parallel for are shared across all threads, even if they are local variables in one of the functions. So we still need to privatize that. Okay. Let me go to the last demo. I'll use our golden solution to do this. I'll not show every single function to you because it's our golden solution. So for this function that we just showed you, find out path, we're doing a for loop that calls the multiple destination Dijkstra using multi-threading here. And I'll comment out multi-threading and get the time. And I will be using the Toronto, easy Toronto. So map completed and we are running it. Traveling courier took 4.788 seconds. And let me multi-thread this. $4.788. $0.72223. See the speed up. Okay. Next. Let me double check my script. Okay. Now, seeing the tests are passed even with multi-threading, let me break the multi-threading by using global variables instead of local. So we have two global variables that we are making into local variables in here. Let me show you the first one. So defining this will make this vector global. Here and make. And this will get a lot of warnings because it breaks something else, but it doesn't have anything to do with our traveling courier, so that's okay. Yeah, just showing a lot of shadow declarations and functions that are not used. We run the exercise again. So it failed. And why does it fail? We have a double free or corruption. So this means there's a memory corruption. Let me try to run the debugger and see what's the bug and where it corrupted. Yeah, compiling with unit test debug and debug the test. And I'll let it run until it crashes. Yeah, crashed. Let's examine the call stack here. And scroll to somewhere we know. We're crashed here, where one of our threads is trying to resize that global variable, that global vector on nodes. And this will go away if we take out the multi-threading. Let's check, will it go away? Make from history. Yeah, so it passes without multi-threading. So that could be one thing to check if your multi-threading is getting wrong results. So by disabling multi-threading, if it passes, then there's some memory that should not be saved, be shared. Let me enable it once more and now, instead of making this one global, I'll make the second one global. And let's see what problem will we get. Make again. So the second one is the priority queue. This one. Intersection is disconnected exiting with path empty. Let's see it from the debugger. We have these many threads, 16 threads, and it doesn't seem to be finishing. So let's pause and go to the call stack. You can see this one is doing some priority queue thing. See, this one is doing some priority queue thing. This one is also doing some priority queue thing. Continue again and pause. We will again get a few threads doing the same priority queue stuff. And we will be stuck inside an infinite loop. Okay. Yeah, so that's just some hints on something could be wrong with priority queue. And again, let me comment out the OpenMP line and let's confirm that it will work without multi-threading. Yeah, it passed. So just to confirm that it will work without multi-threading and the thing was caused by multi-threading. Let me double check. Yeah. That's all for the demo. Any question about the demo? Or is it just clear? Yeah. It searches everywhere, but from a single source. You have to run it for different sources. Yeah. Okay. So recall, to estimate the travel times, you will need to save everything into something like a matrix of all of the from intersections and the to intersections. So if we want to store the results that we get, we have to write everything into a paths matrix, a vector of vector, which is a matrix, and pushing back. So what it will look like is like this. We'll have a vector of paths, and it will point to, each one will be a path from the intersection 1 to intersection 2, or intersection I to intersection J. So if we do this, is this called OK? Because we want to store everything into a single matrix. So the path needs to be shared. So we have to keep the path matrix outside. Then is this code OK? We're looping through all of the sources and we're pushing back. Any thoughts? Pushback will push to the back of the vector. But remember the matrix, right? You want to keep in mind of the index of the from and to. Yeah, because it won't push back in the same order as the indexes. So this will misorder the data. And if two threads are doing the push at the same time, it may reallocation and copy if another one is in the middle of a push. So you might get lost data and or corrupted memory. So what you do is to first, we want to resize everything before going into it, and we are only writing to that specific index. So that we don't mess around with each other. Make sense? So every thread will get its own memory to write to. So in general, how do we debug the parallel programs? The first thing is to disable parallelism and see if the program disappears. If it disappears, then probably something is fighting with each other. Probably a race condition, multiple threads is writing or reading a shared variable. If the problem persists, then probably it's not a parallelism problem. Run in the debugger using the what I just showed you. You can go to the call stack of each thread and see if multiple of them are accessing a same shared variable when we crash. Then fixing the race conditions after you find it, you can either make the variable into a local variable so that each thread has its own copy, or you can use the OpenMP critical to force that section into a critical section. It's usually a not so good solution because it usually costs performance. But if you have to do it, you have to do it. And here is just a way to estimate the amount of speed that we can get from parallelization from this function, from this equation. So this is Amdahl's law. Amdahl's law, it's just saying that your speed up that you can get from parallelization cannot exceed this value. So suppose we have n cores and we have f as the fraction of the work that you are parallelizing. And your speed up will be limited by this. For example, if you have only half of the program to be parallelized, then probably your final speed up will not exceed a 2x or something. So takeaways. First, always improve your algorithm before making them into parallel threads. Add OpenMP pragmas because it's flexible and you can remove them with one line. Avoid modifying shared states. If you have to be really careful. Making something private, so each thread has its own copy, so that they're not interfering with each other. Parallelize large chunks of work because there will be overheads making the threads. So only parallelize those that are really large. And multi-threading is hard, and there are many researchers just to make multi-threading work on some problems. So yeah. And some M4 suggestions. First, get something simple working, like doing the more simple stuff by just doing a simple travel time estimate, simple ordering heuristic, like not doing something fancy that's like simulated annealing at the first place, and get a legal solution first before diving into it to get a better solution. And then you can just start optimizing for your solutions and parallelize only when you think you get the best algorithm you have. Only if you want a further challenge. And yeah, good luck on M4. Any questions? And this will be the last time you see me. If you don't see me during OP2, then this is the last time you'll see me. I'm not sure. I only know my time. Okay.